Okay, great. Okay, Bob, please, you can start.
Okay, well, thank you very much to the organizers. Let me just jump right in. Yeah, so why do we believe in black holes? They are macroscopically large objects, so that makes us think that the low energy effective theory, which is GR, should be enough to describe them, say, other than the singularity. So what can go wrong with that belief? Well, I guess the string theory fuzzball program is the most well-known challenge, and it suggests that the story is not over until we know what the UV complete theory is. So I think there's another good example along these lines from QCD, and that's quark matter. So QCD can have quark matter states that are macroscopically large, for example, quark matter stars. And so we might ask, well, can we learn about these things from the low energy effective theory of QCD? And the answer is no. So quark matter happens when a high enough density of quarks effectively creates a hole in the chiral condensate, phi. But the low energy theory here, it's a chiral Lagrangian, and by definition, phi dagger phi equals 1. So it doesn't see any of this. So what we need is the QCD dynamics that actually describes the variation of phi, such as a linear sigma model. So this last term in this Lagrangian here is such that a large enough quark density can push phi close to 0. So when that happens, you're pushing phi up the side of this potential that costs energy, but there's a energy saving because the quark masses, the constituent quark masses, are basically going to 0 on the inside of this quark matter state. So the basic point is just that the low energy theory doesn't see any of that. So let's try to push this analogy further. What is the analogy of a hole in a condensate for gravity? So we can consider, let's consider the volume element and divided by r squared. That's just the product of these metric functions with a square root. Just remember A here is GRR. So we could consider a hole in space-time to be a region inside some radius where this product is going to 0. And we just don't see such things in GR. So for a black hole, this product is equal to 1 everywhere. And I think that's the analog of phi dagger phi equal 1 in the QCD example. We can add matter to GR for a star, for example. B of R does get small, but A of R typically is larger than 1. And at the origin, A has to equal 1 for a non-singular spacetime. So I'm bringing this up because a 2-2 hole turns out to be this type of hole in space-time, and it only forms for sufficiently large matter density, just like for quark matter. So what UV completion am I talking about? Well, it's quantum quadratic gravity. This was proposed long ago by Stella as a quantum field theory for gravity. It's a simple theory. It has the Einstein term plus a Weyl squared term plus R squared term. And he showed that this theory was renormalizable. And also, at least as far as the C squared term is concerned, it's asymptotically free like QCD. So the C squared term is the important new term here, and the R squared term just basically comes along for the ride. So what I've been looking at recently is how this theory describes ultra-Planckian graviton-graviton scattering. And I'm saying it's quite similar to perturbative QCD. I'm saying this theory produces a parton shower-like description of ultra-Planckian scattering. So in this type of description, what we need are inclusive differential cross-sections for the partons involved. Well, in this case, the partons are the graviparticles of this quantum field theory for gravity. And I'm saying that these inclusive cross-sections are very well behaved, much like their behavior in QCD. So that's all I want to say about this quantum theory, except I'll just point out that unitarity without positivity is really the key feature of this QFT. Okay, let's get back to a hole in space-time. So this this quantum field theory has weak coupling limits in both the IR, which is GR, and the UV because of asymptotic freedom. So the latter means that there's no minimum length and no maximum curvature in the theory. In other words, if this theory could describe space-time or curvature singularities if they exist. So let's consider the classical theory now. It's just the same three terms. I'm saying that this classical theory has some meaning in the far UV because it's close to the quantum theory in the far UV because of asymptotic freedom. And so that's good for these classical solutions that I want to look at because they have interior regions that are ultra-Planckian curvatures. So on the other hand, the classical description may be poor for curvatures around the Planck scale. And as well, the classical theory is unstable. And so we're going to sidestep that a little bit by just only considering static solutions. But these comments mean that the full description of these objects must involve the full quantum field theory. And we're just hoping that the classical description gives us some idea of what's going on. Okay, so we start with the black hole, and it has this no drama horizon, and we don't see anything to do with strong gravity until we go far into the interior. But it leads to some puzzles. What and where is the large entropy? And then there's the information paradox. So a 2-2 hole brings the strong gravity right out to be just beyond where the horizon would be. So that, yeah, there's no horizon in this solution. And the distance that extends beyond that is extremely small, something like the Planck length. So beyond that pink region here, then the Schwarzschild metric describes the metric very well. The other thing about this object is for a particle like a photon to escape, it has to travel very close to the radial direction. It has to lie inside this escape cone. But the angle of this cone is extremely small, Planck length over the size of the object. So it's showing how well this object traps particles. Now, if you look on the inside of a 2-2 hole and look at these metric functions again, these functions are going both like r squared close to the origin. And that's why these things are called 2-2 holes. But we see that the whole metric here is going to 0 like r squared. So right at the origin. And that leads to a naked time-like singularity. And I'll come back to that singularity later. The other thing I can say about this solution is that we know what the interior scaling is for most of the interior, except maybe very close to the edge. So we know what the interior scaling is as a function of the mass or the size of the object. So in terms of these coefficients are scaling like 1 over m to the 4th. So they're getting very small for very large objects. So that's another way to see why the volume inside these objects is getting very small. Well, I can just take a solution and plot this quantity I mentioned, the volume element divided by r squared. That's constant outside the surface of a 2-2 hole. But as you go inside, it falls off a cliff. And the radius of this particular 2-2 hole is 80 Planck units, so still fairly small. The inset here is just showing the same thing on log coordinates. So this is happening because of the way the metric functions are behaving. So the B function is falling quickly at the surface. And more interesting is the way the A function, the GRR component, it grows for the Schwarzschild solution, but as you just get inside, it also falls off a cliff. So I said these things only form if you have sufficient density of matter. And we can just be talking about a relativistic gas, a standard relativistic gas. And I think this is the realistic case. This gas will have a temperature as a function of R. It's going like the inverse square root of the B function. times some constant, which we call T infinity. So the field equations, they are cumbersome to deal with, but they, in the end, they do determine these metric functions, and as well, a particular combination of constants. So n counts the particle degrees of freedom in nature, and m2 is the mass of the massive spin 2 particle in the quantum field theory. So there are a couple exact results. The total matter energy is just 3/8 times the total mass. And the entropy, I'll show you where it comes from. The entropy of the 2-2 hole times this T infinity is, that product is exactly the same as the corresponding product for a black hole. So if you look at the temperature, which will play a role in calculating the entropy, it jumps quickly at the surface and eventually diverges at the origin. So because of this behavior, you could call this thing either a fireball or a firewall. So it diverges, but the entropy integral we have to do, which involves this thing to the cube, this integrand is actually finite. And the integral here gives something that goes like the area. In other words, like m squared. And in fact, the result is just some constant times the black hole result. So just to show you what this integrand is, it's like this. So yes, it's finite everywhere. It's not totally concentrated at the surface or anything. It's spread right to the origin. And so why do we get an area law out of this? Well, it's because of how A and B scale with M. And I mentioned how that works before. So that's the origin of the area law. And this constant is this, which depends on the number of species in this way. But the number of species for the standard model is well over 100. So if the M2 mass is of order of the Planck scale, which is what I expect, then this constant can easily be larger than 1, in which case the entropy for the 2-2 hole can be somewhat larger than the entropy for a black hole, and T infinity somewhat less than the Hawking temperature. So in this situation, we have a counterexample to standard entropy bounds. So let's talk about the dependence on this number of species. Well, the black hole has no such dependence. Well, let's also consider just a box of particles, a relativistic gas involving these n species of size r, and assuming it does not collapse to a black hole, that generates a bound for the amount of entropy that that box can contain, which is given by this. And you see here that the black hole entropy is not necessarily larger than the box entropy, because of if n is arbitrary, if it's arbitrarily large, then the box entropy can be larger. And this is, it could be called some kind of species problem. The entropy for a 2-2 hole, though, has this n to the 1/4 built in. And it's clear that this entropy here is larger than this one, and as we've already mentioned, larger than the black hole. So yeah, you could say there's no species problem for 2-2 holes. We could also think about modifying the generalized second law. So the total entropy would be the entropy outside plus now the 2-2 hole entropy. And so the second law would say that this total entropy never decreases. And so that would also imply that a 2-2 hole cannot be converted to a black hole because you would be lowering this quantity. Here's another plot of the integrand of something, in this case, the action. And it turns out the Weyl squared term dominates the action inside a 2-2 hole. And it looks like this. So quite unlike the corresponding result for in the Schwarzschild solution. So yeah, you could say that the 2-2 hole is a ball of viral action. Okay, now we're heading towards gravitational waves. So let's start with the wave equation. And that brings in this question about a singularity at r equals 0. So what does that do to the wave equation? Well, surprisingly, it makes the wave equation even less singular than the wave equation in spherical coordinates in flat space. So looking at the simple scalar wave equation, it has the standard angular momentum term, which is singular at the origin, but in the 2-2 hole, B of r is behaving like r squared at the origin. So this is now finite. So that means that all waves for any L behave like S waves. And so all waves penetrate right to the origin. But other than that, it's very familiar to us. There's just one finite energy solution for every L. And so that means there's the unique solution that has to be chosen, which means there's a boundary condition at r equals 0. And so, I'm going to make use of that boundary condition later. So basically, the singularity here introduces no ambiguity or ill-defined time evolution or energy non-conservation. Okay, moving on to the gravitational wave equation. In tortoise coordinates, I think we've seen this before. It's expressed in terms of a potential, and for a black hole, that potential is really just a potential barrier around the light ring radius. And in these coordinates, you have to go off to minus infinity to reach the horizon. For 2-2 holes, waves have a finite travel time to the origin. So effectively, there is a boundary at a finite tortoise coordinate, which is just at r equals 0 due to our boundary condition. You could call that a wall if you want, but because of it, we have a cavity structure. And so waves that bounce back and forth in the cavity, because this potential barrier on this side can leak, this is what generates echoes. Okay, so the size of our cavity in tortoise coordinates is delta x, and the round trip travel time in the cavity, the time delay, delta t, is just twice delta x because of our use of tortoise coordinates. So comparing this potential for a 2-2 hole to some other objects, first of all, the 2-2 hole is in red here, and it matches the black everywhere else. But here's the surface of the 2-2 hole. So to the left is what's going on in the interior of a 2-2 hole. And all the diverging curvatures and all that stuff is just giving a very small defect in this potential. So it's very unlike a very compact star, which would have this angular momentum blowing up part of the potential. And so a 2-2 hole is much more like a truncated black hole, where you just take the black hole case and just truncate it at some finite tortoise coordinate. And that's called a truncated black hole. And you could describe it as saying there's an artificial wall just placed just outside the horizon. So the point is the truncated black hole gives a pretty good approximation to a 2-2 hole. And that's good because in the spinning case, we don't actually have spinning 2-2 hole solutions. So in that case, we're just going to use the truncated Kerr black hole as an approximation. Now the time delay, delta t is actually larger than what I've indicated on that plot. It's large because of this large log enhancement. The spin and the redshift also tends to enhance it. And in the realistic case, you can get something maybe closer to 800, which is 10 times larger than what I showed here. So in that larger cavity case, the size of the interior region of the 2-2 hole stays about the same. So it now takes up maybe 1/10 less of the total size of the cavity. Okay, so this large log reflects extreme compactness with this wall effectively at a distance just slightly outside the horizon. This distance is delta r, and this distance delta r is awarded the proper Planck length if this quantity eta that I've introduced here is around 2. But estimating eta for large 2-2 holes is not easy. This is a numerical problem. So eta is one of these things that we actually don't know how it scales exactly as a function of m. So we can just take our smaller 2-2 hole solution that we actually have and try to extrapolate to large masses. And that shows that eta can maybe be around 2 or somewhat less. Now, getting to the echo waveform, an actively studied problem is to drop a test particle into a truncated curved black hole and study the emitted gravitational waves. And this will include echoes. So that's a well-defined problem, and several groups are working on it. The trouble is that this picture is rather far from the merger of two similar-sized black holes. So instead, we can imagine a truncated curved black hole just being in some excited state just right after its formation, and just explore that situation for a range of some initial conditions. So these initial conditions would be perturbations, either inside the cavity or outside the cavity. And I'm going to treat these two cases separately. So we're after the echo waveform, which is the gravitational strain waveform h of t, or we can consider this in frequency space h of omega. Now I'm suppressing all the angular information here. So in a Green's function approach, h of omega is just given by some transfer function times something called the source integral, which we're just going to take from the initial condition. So the transfer function is well known and well studied. It contains the spectrum, and it has this nice formula in terms of quantities that we already know from the curved black hole. So the transmission and reflection amplitudes here. And omega 0 is the Kerr frequency. And the cavity structure brings in this delta x, and it brings in R wall, which is telling you how the wave interacts with that inner wall. Well, in our case, this R wall, not just in our case, in general, the absolute value of R wall gives the ratio of the outgoing and ingoing energies. But I've already mentioned in our case, the boundary condition is such that these things are equal. So the absolute value of R wall is 1 in our case. On the other hand, it's known that R Kerr absolute value is slightly bigger than 1 in this frequency range. And that can lead to echoes that would just keep growing. And so some damping is going to be needed. And I will come back to that. But the formula in its current state does not contain that damping. So here's a picture of the transfer function. It's a very dense set of these resonances. And these resonances are so closely spaced, the spacing is so small delta f because it's 1 over delta t, and I've already explained why delta t is so large. So let's start with a perturbation inside the cavity. Let's characterize it by a function f omega, which determines the energy flux of this perturbation in terms of the frequency. So when you use this function f omega and look at this final result for the absolute value of h omega, you get a very simple result. It's the transfer function times f of omega times a new factor, omega minus omega 0. I'll just call this a difference factor. And this whole result is surprisingly simple. In fact, there's a lot of complicated stuff that has been canceled in getting here. And this new factor then suppresses the largest part of the transfer function. So the result then looks something like this, where there's this new 0 right where the peak would have been. So that's the effect of this new factor. Meanwhile, this negative frequency bump depends on my choice of f of omega. And I think maybe more realistically, this f of omega will yield a negative frequency bump, which is somewhat smaller than what I've shown here. In any case, a 3-bump structure of this type is going to lead to echoes with quite an irregular shape, and so not easy to model directly. So let's move to a perturbation outside the cavity and just do the same thing. Now we introduce a function g of omega. And here the result is even simpler and rather surprising. The result here is just that what comes out is just this function that I put in, and not even the transfer function appears. So that means that all the resonances are completely gone. Well, this is for the special case of exactly real omega. And it's also assuming our model case where this is 1 as well. So that's for real omega. So on the complex plane, the poles are still there. And what's going on here is that this source function is bringing in a set of zeros, such that each pole is matched by a 0 on the opposite side of the real axis. So that means if you sit right on the real axis, there's a cancellation between the zeros and the poles. So that's fine, but on the other hand, to get back to the time domain, we have to do an inverse Laplace transform. And that then ends up picking up some effect of those poles in the complex plane that are still there. But it picks up the poles that are not so close to their zeros, which leads to a small result. So it picks up poles that are further from the real axis. And so the difference is larger and you get some effect. But those are the poles that correspond to wider resonances, because the pole is further from the real axis. And so this whole end result then is that the echoes that come out of this situation tend to die off quickly, because it's really only the wider resonances that survive. So putting all this together, for both the inside and the outside cases, I'm saying that there's a suppression of the echo spectrum around omega 0. And in particular for the outside case, there's also a suppression of all the narrow resonances. Now, if we go back to the actively studied case of a particle falling in, that's more similar to the outside case that I'm talking about. And there have been some recent numerical results that are showing both of the types of suppression that I'm talking about. So that's coming from this paper here. And so one of their plots is this. So if the blue lines are just showing some older result. So let's look at the orange curves. And so first of all, we see this suppression that I'm talking about at omega 0. And then in this region here, this is where the very narrow resonances tend to sit. And we're seeing quite a strong suppression here. So I think that agrees quite well with what I'm talking about. And so at first sight, this doesn't look very good for a search for echoes, because it seems like there's these new sources of suppression. But I don't think that's completely right. I think there is a good remaining hope for strong, slowly decaying echoes. And that can occur as long as there are some perturbations inside the cavity at the time of formation of these kinds of objects. And I see no reason why that should not occur. So I still have a lot of hope for an echo search. One last thing I can do here is just to generate some kind of random initial condition inside the cavity. And we see from this that the resonance structure is still there. It's just a lot more ragged looking, but it's still there. Meanwhile, if you go to the time domain, then the echo structure is basically gone. And so this example tends to show that the echo search at LIGO should actually be a resonance search. And now, if I have some time left, I just want to say some things about the damping. So I've mentioned if there's no damping, that there are these instabilities which can lead to growing echo signals, which, by the way, may not be completely unphysical. You are extracting energy from the rotation, and so something would eventually have to happen, some explosion or something. But if we want to avoid all that, we have to go beyond this truncated black hole model with some perfect reflection. Many authors are considering ways to do that. So I just want to point out here that tutu holes provide a very well-defined system to study damping. So gravitational waves are just propagating through a normal relativistic gas in the interior of the tutu hole. And remember that this interior is just sitting at one end of the cavity. So we can start with the Hawking formula for the rate of energy loss due to a wave propagating through some medium with some viscosity. And so we can write this formula in terms of viscosity to entropy density ratio, V times the entropy density S. Now we can rewrite that and get something called R damp, which will be the damping occurring over one round trip of the wave inside the cavity, and such that R damp equals 1 when there's no damping. So we end up with this exponent with this integral, but this integral is very close to what we already did to get the total entropy. We're talking about an entropy density here. So the difference is that this integral gives the total entropy divided by the area, which is what we just said before was a constant. So this would give a damping factor, which is very simple looking, and in fact looks very well known because this viscosity ratio is bounded from below by 1/4 pi. So this all looks very nice, but it's not right. It's missing two important effects. One of them is that the Hawking formula should be supplemented by some frequency-dependent suppression factor. So it depends on the frequency and this other quantity, which is the collisional frequency. And you can see if the wave frequency is much larger than the collisional frequency of the particles in the gas, then this acts as a suppression factor. And so this factor is here because it's the period of the wave which limits the time that a particle can react to the wave when this time is less than the collision time. So that's why this factor is there. And in the final result here, it introduces a factor which does suppress the amount of damping when omega is large. So how large? Well, here's the result so far, and it gives this green curve. So you see that the damping gets very substantial for these small frequencies. So that's one of the two effects that we haven't put in yet. And the other effect has to do with the very poor overlap between the energy density profile of the waves, or the quasi-normal modes inside the cavity, which, remember, have to satisfy that boundary condition, effectively saying that the wave vanishes at the boundary. So the overlap between that and the entropy density profile of the matter in the cavity. And we said that the entropy density is sitting at one end of the cavity. So the fact that these things may or may not have a good overlap gives this blue curve. So the damping has been reduced. It still mainly just occurs at low frequency. So that's for a static black hole or tutu hole. We'd like to extend and extrapolate to the Kerr case, where omega 0 is not 0. And now we're interested in the fact that, as I mentioned, this R Kerr is somewhat larger than 1. So we can consider the product of the new R damp times this R Kerr. And what we see here is this is now less than 1 everywhere. So the damping in this case is large enough to cure the instability. And we also see that the damping now mostly just occurs around omega 0. So the end result then is that there's just an extra little bit of damping in the region around omega 0 in this range here. But as I've already mentioned, that region was already suppressed by this factor. So it just makes this small region for the resonances somewhat larger. Okay, I think that's all I need to say about what I want. So I can get to the conclusion, which is just how two holes compare to black holes. So they're very similar in many ways. There's no upper limit on their size, the negative heat capacity, a very cold dark body, maybe even somewhat colder than a black hole, and an area law entropy, with entropy somewhat larger. But in many other ways, they're very different from black holes. Matter is not lost to the singularity. Matter is the source of the whole solution. Information does not leak out. It does slightly leak out. And the singularity ends up producing a very simple 1D cavity structure for the wave equation. And this yields gravitational wave echoes. And it yields a very closely spaced spectrum, which reflects the extreme compactness of a two hole. Okay, thank you. That's all I want to say.
Thank you very much, Bob. So we have 2-3 minutes for question. So please, if you have any question, please can raise your hand. If not, I have a couple of questions. Maybe I can ask one now and maybe another one during the discussion. So you mentioned that the entropy of this two hole is larger than the like partial black hole entropy. So of course here you're just showing like static solution, but for instance, you said that this entropy cannot become like smaller than, cannot become one of the black hole, because otherwise you would violate the second law that you show in some of the slides. Does this mean, I mean, this argument that maybe you can say that like thanks to this generalized second law, like you can avoid like some dynamical process, some instability that would take you like from two hole to some collapse and form a black hole?
Yes, I think so.
Okay, I see. And you think, I mean, that, so, okay. So even dynamically, you never form, like, you never go from a two hole to some black hole configuration. So it would be stable against collapse because of that second law.
Yeah, that's the conjecture.
I see. Any other question? Okay, since we are anyway a bit beyond the scheduled time, maybe we can have like exactly 10 minutes of break, and then we can meet again to have the final discussion session of the day. Okay, so thank you very much again, Bob, and see you in 10 minutes.